So our topic is polar coordinates, and if you're following along in the Thomas textbook, this corresponds to sections 11.3, 11.4, and 11.5. They divide it up a lot. I know it sounds like we're taking a lot of sections all at once. They divide it up probably a little bit too much, so really this all fits together as kind of one topic. So what this topic is about is it forces us to think about how we've described the position of a point in the past. Normally, when we describe the position of a point, we describe it as you see on the left in what's called Cartesian coordinates. We write that this is the point AB. But if you think about what we're really doing, is we're saying, let's start at some point that we call the origin, and let's walk a certain amount in the horizontal direction, and then once we get there, let's walk a certain amount in the vertical direction. Actually, it doesn't matter whether you do vertical or horizontal first or second. The point is that the position AB is saying we start at the origin, we walk A units to the right, and then we walk B units up. And then, of course, if we had, some point that was in this territory here, like let's say that that's like -2 comma -2, what we'd really be saying is we walk -2 units to the right and -2 units up, which of course corresponds to left and down because we're walking, -2 units to the right, which is like walking +2 units to the left. So the point is that's the system that we use to describe the position of this purple point here, which I'll highlight in yellow. We describe the position of that point in this way. The However, there's nothing special about that system of describing the position of a point, and sometimes there's a more convenient way. There are other convenient ways to describe the position of a point. So it turns out that all you really need to describe the position of a point in the plane is you just need two types of motion that are significantly different from each other. If I were to say that I'm going to describe it by the following two things, how many steps I take to the right and how many running leaps I take to the right, that wouldn't work because the only direction I'd be able to move is right or in the negative direction to the left, but I'd have no ability to move up or down. As soon as I add that there's the concept of moving to the right and then moving in some other direction, such as up, then I can get to the point. So consider the following method of describing the position of a point. Let's suppose that we ask how far the point is from the origin, and just set that. We're going to ask how far the point is from the origin, and we're going to call that distance, we're going to call that distance r for radius. And then we're going to ask also how many degrees, or radians rather, we have to turn from the positive horizontal axis in order to get there. This, it turns out, will perfectly well describe the position of the point. We're describing it by the angle, how much we turn from the horizontal position, and then how far we walk out from the origin once we've decided what the angle is. And we can describe the position of this point as r comma theta. In other words, this is now a pair of sufficiently different types of motion. One of them is radial, and one of them is angular motion, meaning how much we rotate around the origin, and the other is what's called radial motion, which is then once we've decided how far to rotate around the origin, how much to rotate around the origin, we decide how far to walk out from the origin. So, like I said, the as long as we have two types of motion that are sufficiently different from each other, we can describe the position of a point, and we're going to be using this method, which is called polar coordinates. This is called the polar coordinates. I know I've written that already, but I just want to write it near the diagram of it. And this concept that I sort of tried to describe in very general terms of you need two types of motion that are sufficiently different from each other. Just to give you a little preview, at some point, some of you I know are computer science majors. At some point, you will take a course called linear algebra, and there is a name for that concept. The concept that I described of having two sufficiently different types of motion is what's called linear independence in the subject of linear algebra. Okay. One thing that may bring us a little bit more into focus is if you consider the type of graph paper that you normally use. I know I've done this in very not very neatly, but what I've written on the left is sort of supposed to be suggestive of the graph paper that was probably handed out to you in middle school or high school on which to graph curves and points. It has this kind of grid. The blue lines are of course the x and y axes. You can write them in like that. These are x and y axes, and then there were these sort of lighter lines that I've written in purple that indicate units moved in either the horizontal or vertical direction. So on the right side, what we would have is we would have for polar graph paper, the equivalent grid would be concentric circles and radial lines. So in other words, the concentric circles indicate really the distance that we're moving away from the origin. That's going to be the radius. And then these lines like this indicate what the angle, they indicate the angle from the origin. So you might call that like 30 degrees, 60 degrees, 90 degrees, although we'd usually do this in radians, of course. But the point is that this is sort of the equivalent graph paper showing, showing the two relevant directions that you need, the two relevant types of motion that you need to describe the position of a point.